Hello everyone, for this tutorial video, I'd like to explain double integrals using polar coordinates rather than rectangular coordinates. In particular, we can derive a formula using double integrals by remembering that for polar coordinates from Calculus 2, the angle of a polar function is between a specific value alpha and a specific value beta, and that the radius or distance from the center is between two curves as illustrated in this graph. So now, with some creative thinking, if we break down this area into a bunch of rectangular arcs like you see on a fan, then the area of one of these rectangles is one length given by the outer arc length, one length given by the inner arc length, and the width given on both sides by the change in radius between these 2 points. So now, if we take these rectangles infinitesimally small, we can assume that the inner and outer radiuses are about the same. So this means a change in area equals the radius times the change in angle times the change in radius. And using differentials from Calc 1, we can see that dA is about the change in A, and the same is true for the angle and radius. So we conclude that dA equals radius times d angle times d radius. So now we substitute this in the double integral formula where the change in A is. And also remember that to convert from rectangular to polar coordinates, x is radius times cosine of angle and y is radius times sine of angle. So we plug those in to the function where we originally had x comma y. And we conclude that this is the definitive formula for a double integral in polar coordinates. So if we have a double integral like this, and we are told to find the portion between a radius of 2 and a radius of 5 in the first quadrant, we would do this by first stating that the radius is between 2 and 5, and that in the first quadrant the degree is between 0 and 90, or 0 and pi half, by definition of what the first quadrant is from trig. So now we use the formula we derived and plug in these values for the limits of integration. However, even though we correctly use the substitution, we can actually simplify what we are integrating using a trig identity. And so we do that. We take the first integral on the inside, which was the integral of the radius, and then we take the next integral of the degree. After we finish our work, we conclude that the exact area is 609 over 4. Now that we have comprehensively gone over how double integrals work and applications of them, we can move on to definitions of triple integrals next, or integrals of functions with 3 inputs. Don't forget to subscribe if you found this video informative, and make sure to see other tutorial videos, and follow me on either Facebook or Twitter for more content.